Hello students, in today's lecture we will continue the same module, that is the future of urban ecosystem, and we will be discussing using the case studies on the eco-engineering solutions for waste, energy and water management. So we will be discussing the eco-engineering. I hope you remember we discussed the NBS and one of the vertical under that nature-based solution is the eco-engineering. We will discuss typologies of intervention, the biological engine, the technological nexus, high-tech closed loops and waste-to-energy model. And finally, we will sign off with the operational guideline. Ecological engineering, the philosophical foundation of this concept is integration of human society with its natural environment for the benefit of both. Self-design auto-organization is one of its key feature. Designers set initial conditions like basin shape, hydrology, and nature selects the species mix, and then it continuously evolves further. Solar-based it is, powered by sunlight, photosynthesis rather than fossil fuels, electricity. It follows the system approach, treats the catchment, not just the end of pipe. Ecosystem conservation is one of the major benefits of this ecological engineering as it provides habitat for birds, fish and etc. while performing engineering work like cleaning water or treating the waste. So, it is very pertinent here and relevant here to discuss again the linear versus the circular metabolism. We know that we have to say no to linear metabolism, which actually believes in the principle of take, make use of it, and create waste. And that's the model linear economy, resource extraction, production, distribution, consumption, and then the waste is going to the landfill. Whereas circular metabolism, the eco engineering goal is something different as it mimics the biological nutrient cycles. Waste is a resource, so it's a very strong shift in the ideology because it is input for the next cycle and it results in regenerative loops, reduce the externalities. And you can see here the production, distribution, consumption, reuse of it or repair or recycle and then recycling sector, and again it is coming into the production. The typologies of intervention as discussed earlier, biological, technological, and we will also discuss the closed loop, high tech and waste to energy model. First one, the biological engine, where we will be discussing the municipal sewage waste. And the case study is the East Kolkata wetlands. By now, all of us, we know this particular case very well. I hope you people are following the case as well. The East Kolkata wetland is the kidney of Kolkata. It actually filters the waste of the city. Ramsar site is having a 12,000 plus hectares peri-urban ecosystem, world's largest wastewater fed aquaculture system. It treats 900 to 980 million liters per day MLDs of Kolkata's sewage, and it saves almost equivalent to 22 million USD per year in STP operating cost. Engineering the process in this particular case is the solar powered waste treatment. Algae bacterial symbiosis is the mechanism, and sewage is diverted to shallow oxidation ponds, whereas it's called in the local language. Depth is being managed around 50 to 150 centimeter to ensure sunlight penetration. And the cycle is like photosynthesis. Algae produces the oxygen, and this oxygen is being used by the bacteria to break down the organic waste. And fish will eat the planktons, algae, bacteria, biomass, whatever is getting generated, that is the harvest. So we can find that the waste is becoming the protein or food for the fish. Does it work? Quantitative diagnosis says yes. BOD, high organic load, almost 60 to 95% efficiency we can find there. Microbial oxidation is the process. Coliform, high pathogen, 99% plus is the reduction rate. UV radiation and predation. Ammonia 10 to 29 milligram per liter is the incoming influent ammonia content. 80% is getting reduced. Plant uptake, nitrification, all around these varies. There will be lot of vegetables coming up. Phosphates are very high and 90% removal efficiency we can find through the algal assimilation. And during the winter time, due to this lower microbial activity and less sun, performance dips slightly. Carbon dynamics in this particular wetland, the carbon sink it's not only the water, sewage water getting treated. Soil organic carbon, we can find that recent 2024 studies are confirming this East Kolkata wetland is acting as a significant carbon sink. Sewage fed nature enhances the soil organic carbon sequestration compared to freshwater ponds. We have discussed this previously also, that both the mangroves as well as the wetlands, how strong they are in this sequestration. Nutrient enrichment leads to higher biomass accumulation in sediments. This East Kolkata wetland is also helping us a lot in climate mitigation. It locks the carbon that would otherwise be released as methane or carbon dioxide. But there are again threats and governance. The vulnerability of the biological system is there, and also the physical system being protected. That problem is also there. In the biological system, we can find that land use change is happening every time and very rapidly. 91 to 2023, the wetland area has decreased from 91 plus square kilometer to 33.4 square kilometer, whereas the built up area has increased from zero point 0.2 square kilometer to 10.5 square kilometer. So just see how many times that built up area has increased, 0.2 to 10.5. The governance failure, salami slicing of land for real estate, lot of pressure from the real estate side, fragmented enforcement between the Ramsar guidelines and local municipal needs. So the lesson learned from these particular cases, biological solutions require land protection as a core infrastructure requirement. Otherwise, it cannot solve. Next, a point we'll be discussing, that's the technological nexus. The solid waste is going to be our focus. And in this case, we have selected the Hammarby Sjöstad from Stockholm, and basic concept to be discussed is integrated infrastructure. This Hammarby model, the EcoCycle 1.0, is unifying energy, water, and waste flows. 50% reduction in environmental impact is the goal when you compare it with the standard housing. What happens? You have your built mass here, and from the lake you are getting the drinking water, it is being treated. The entire habitat is using it, wastewater is flowing out, and this wastewater is getting treated. So you can see that the treated water is coming to some other use, and then ultimately it is coming to the sea water, but after treatment only. And the heat and power plant heat pump is also using the presence of the sea next to it in the electricity. Likewise, you will find when you read this particular image carefully that for everything, electricity, heat, fuel, soil, digested sludge, everything is trying to get recirculated as much as possible. And hazardous waste and all these things are being managed appropriately. So quality is not being compromised, but at the same time, lot of closed loop facilities have been created, and it is having a very strong relevance to our modern Indian smart cities to learn from, like Gift City. This particular Hammarby case also teaches us the energy loop, which is a closed loop in this particular case. Thermodynamics of the city is from the west, we are also recovering the heat. So as I was showing previously also, every time the heat pump is gaining the heat from the flow of the water also. So waste to heat, combustible waste incinerated in district heating, wastewater to energy, heat pumps extract the thermal energy from the treated sewage effluent, biogas from sludge digestion, fuel buses and the household stoves. So this is a very strong circular loop we can see here. District cooling, you can find here the water, the rain is locally treated, sewage is cleaned, and biogas is there. Biogas, heat, and fertilizer is the outcome of that. Waste, recycle energy, and fertilizer energy is heat and electricity. And district cooling, we can find that cold water post heat extraction is used for the cooling networks. So nothing is going waste. Everything is having a purpose there at each and every stage. This is also brought the invisible infrastructure in front of us, such as the NVAC automated waste collection. We can see that pneumatic, actually they are having the pneumatic underground tubes. You can only find this interfaces on top. Operation was sorted into fractions, organic, combustible, and the recyclable, transported by vacuum at the 70 km per hour to the peripheral stations. So, as a citizen, you need to only use this, but as the waste is getting segregated and it is being tunneled to requisite place where it will be treated. No heavy garbage trucks in the residential areas. So safety and noise aspect has been taken care. Higher segregation rates due to ease of use. Operationalizing smart infrastructure in India, we are also working on it, and Gift City will be a very good example to see that many such positive things have been integrated. India's first operational smart city, Gift City, district cooling system capacity is 10,000 tons of refrigerations, and the planning is 1,80,000. It is using 30% less energy than individual building ACs. So it's a very strong shift from the individual decentralized AC system to the centralized city level cooling system. Thermal energy storage, stratified tank store chilled water at night or peak for use during the day. And significance is that it reduces urban heat island effect by eliminating external AC condenser units. Yeah, you can see that also for the waste, what it has done, automated the waste, adapting the Hammarby model, NVAC system implementation, India's first city scale pneumatic waste system. 400 tons per day, it is planned. Waste travels at 90 km per hour through the underground pipes. You can see the solid waste pipe, potable water, and the city level fire water. All the waters are on the our level, and this waste is at this level, and at the lower level we are having the chilled water return. So once that extracted heat has been extracted, chilled water is coming back, and it is replacing 80 waste collection trucks, minimizes human contact with waste, hygiene and safety has improved, real time monitoring via the city command center. The high-tech closed loop wastewater we'll be discussing now. Singapore is the case. We have discussed it previously also. The four national taps, you remember. First one is the local catchment water, imported water from Malaysia, and new water and desalinated water. These are the four taps based on which Singapore's water policy stands. Existential scarcity, no natural aquifers, limited land. So the city, the state can know, the country knows its problem. So it is having this imported water, local catchment, urban stormwater, new water, high grade reclaimed water, and desalinated water. Focus is new water as the ultimate circular loop example. Triple barrier engineering, microfiltration. If you remember, we have discussed this previously also. But let us go through it once again. Microfiltration, which removes suspended solids or bacteria. Reverse osmosis, the core barrier, removes the viruses, heavy metals, and the dissolved salts. And ultraviolet disinfection, the final safety guarantee. So once all these stages have been done, then that water is bottled and packed and for ready for sale. Usage primarily for industries, wafer fabrications, and commercial cooling. Indirect potable reuse, like blended into reservoirs during the dry spells. The city state of Singapore has the industrial mandates. So the policy engineering is based on the challenge that the non-domestic sector is expected to account for 60% of water demand by 2065. So 2024 mandates are wafer fabrication plants must recycle minimum 50% of water. Water efficiency fund has been created. Cap is raised to Singaporean dollar 5 million to support on-site recycling plants, where electronics achieved a 75% recycling rate. Singapore Smart Water Grid, it is instrumented monitoring once again, and the problem is leaks in underground pipes, non-revenue water. That is the problem which this monitoring will be addressing. The solution is acoustic sensors. 1200 plus sensors monitoring noise signatures in the pipes. Predictive AI has been utilized. Algorithms detect hiss, that sound, that noise of developing leaks before a burst occurs, and the result is 5 leaks per 100 kilometer, among the lowest globally they are having, because they are not only monitoring it, they are also understanding where the problem may rise. Wherever the risk is, they are trying to mitigate that risk. The energy water nexus, the cost of circularity, energy intensity, both the reverse osmosis and desalination are energy hungry. Pricing as a tool. The water price increased in 2024 by 50 cents per cubic meter to reflect rising energy cost. The logic is price reflects the marginal cost of the next drop, desalination or new water, not the cheapest drop, rain. So that's the way the society is ready to face. They are having a very strong adaptation strategy. The reality check, producing water from the sea, desalination, is nearly 20 times more energy intensive than catching rain. This data point reinforces why Singapore prioritizes local catchment and new water over desalination wherever possible. The waste to energy model, IIT Gandhinagar, the low energy tech, eco engineering in action, zero discharge campus, 100% water recycling. Jal Mandaps, Jal Mandaps have been created, 50 lakh liter rainwater storage integrated into social spaces. Root zone treatment system uses Kana Indica plants for sewage treatment, low energy, no chemical inputs. Passive cooling, PDC towers, passive downdraft evaporative cooling. You can find a similar example also in IIT Kanpur campus. Cools air using the micron sized mist, reducing air conditioning load significantly because the input air is actually now being cooled enough. In the Auroville, we can learn the vortex system, which has been commercially applied in many places as well. Biomimicry in wastewater, vortex diverts, spiraling flow oxygenates water without the need of electrical aeration pumps. BOD reduction is 92% around that, and COD reduction is also 60%. So, decentralized clusters treating sewage for agricultural reuse, these are a very good application potential for this vortex system. IIT Madras also doing a lot towards this industrial effluence, solving toxicity, textile dye effluence, high TDS, toxic, and electrochemical ozone oxidation. That is the innovation, and the benefit is degrades the recalcitrant dyes without sludge. reduces load on RO system by 75%, enables zero liquid discharge in textile clusters. So this is a very strong performance record, I will say, for the system. Now let us go for the once we have seen many such good examples and applications, I hope we are quite excited to understand how these operations can be really happening and scale up. So, these operational guidelines to eco engineering projects, let us have a discussion there as well. There is no silver bullet, land rich or capital poor. If the combination is like that, then one may prioritize biological systems like wetlands, root zone system, like Indian tier 2 cities, peri-urban zones. They can go for it. But there can be certain other cases where land poor but capital rich. Prioritize integrated technology like DCS, membranes, etc. Mumbai, Gift City, Singapore are the good example for this. Social capital, waste to energy, only works where segregation is enforced. Other than that, your return investment is very low because waste cannot give you the energy, quality energy which can be used. The water nexus thinking, the operational guideline, the second phase we are interested to discuss the nexus thinking, the water energy equation. Never design a water system without calculating its energy cost. In Singapore, closing the loop requires energy pricing to support reverse osmosis. In the gift city, district cooling saves energy but requires massive water for cooling towers handled by recycled sewage water. So the optimization is very much necessary. The calibration use treated wastewater for cooling or heating to balance the equation. From concept to instrumentation, the data is important. The future is measured like in Singapore, 1200 acoustic sensors for leaks, or in Gift City, command and control centers monitoring 70,000 input output points. And the design requirement, the infrastructure must include sensors from day one. The fourth and foremost one I will say is the governance. Institutional infrastructure needs proper governance. Physical infrastructure fails without governance. We have seen that in East Kolkata wetland, where we can see that it is failing due to lack of land use enforcement. Real estate pressure is too much there. The engineer's role must design for enforceability and maintainability, not just hydraulic capacity. So we can conclude like that we are moving from linear to circular, static to dynamic. We are going for instrumented one, and we are not believing in disposal. We are trying to recover as much as possible from the waste. The new toolkit, biological engines, wetlands, smart grids, water or energy, social contracts, segregation. These are very important things to follow, maintain, practice. So, today we have discussed the ecological engineering, typologies of intervention, and the operational guidelines to make sure that ecological engineering not only gets implemented but also maintained. These are the list of references. Thank you.